As we've been studying relativity, one of our recent topics has been conservation of form momentum. Now, as you remember, form momentum is a four-component relativistic mathematical object, kind of like a vector. It's a four-vector. The first component, the time-like component, is the energy of an object, and then the three x, y, and z components are px, py, and pz, the momentum of your object through space. So it's a four-vector. And as we've seen, there's this great conservation principle in relativity that says that the total form momentum of your system before some collision or interaction is equal to the total form momentum afterward, component by component. So the first component equality will be conservation of energy, and then the three middle ones will be conservation of the momentum vector. So that's our relativistic idea of form momentum, and I want to apply this to an example from particle physics. In particular, we're going to start off with a kaon at rest. Kaon is a particle that has a rest mass of 498 MeV. We're looking at the kaon in its own rest frame, presumably reproduced in some sort of particle accelerator or something, but in its own rest frame, it's sitting at rest, and at some moment, it decays. That kaon decays, and what we observe come out are a pion, a pi plus in particular, and a muon. A pion has a mass of 140 MeV over c squared, c equals 1, and a muon has a mass of 106 MeV, and so the kaon has split into these two pieces. We're going to choose our plus x direction to be the direction that the pion has gone, and it turns out the muon will go in the minus x direction in this particular example that we're claiming to have observed. So in this example, what I want to do, I want to know, is there anything, do we understand the whole story in this, or is there anything missing that our particle detectors might have missed? So in particular, I know that I can look at the masses and I can say, well, a pion has a mass of 140, muon 106 MeV, so add those together, that's 246, that's less than 498, you'd say, oh, we're missing some mass. But remember, in relativity, mass by itself is not necessarily a conserved quantity before and after. We know that mass is just one manifestation of energy, and it's energy that's conserved. In our particular decay, the pion shoots out with a momentum in the plus x direction of 200 MeV. MeV over c, but c equals 1. And the muon, in our particular decay, shoots out with a momentum of minus 80 MeV. And so we know they're both moving with very high speed compared to, very high speed, so that because their momentum is close to their rest mass. And so relativistically, it's not obvious at first glance, is it going to be that our mass, that our total energy, including both mass energy and energy of motion, maybe that will add up to the 498 MeV that we have for this pion. So, or for the kaon rather. So what do we do with this? How do I analyze this? Well, what I'm going to do, we can do it with equations, and we will in a minute. But I want to start with this very nice conceptual way of thinking about this based on an energy momentum diagram. And energy momentum diagrams are very similar to space-time diagrams that we've used previously. It's got a vertical axis that is energy measured in MeV, and the horizontal axis will be momentum, well, px, x component momentum, since that's what we're looking at right now. Px is here, and so what we want to do, we want to use this diagram to plot out the form momenta of our the various pieces of our system. All right, so what do we get from this? Well, we know that, I should say, this looks like weird graph paper. I'm doing this on hyperbola graph paper, which I got from my colleague Tom Moore at Pomona College. And the idea of the hyperbola graph paper, as we've seen with space-time diagrams, is that the hyperbolas encode constants in relativity. So in particular, on an energy momentum diagram, the 100 MeV hyperbola here, the one that goes through 100 MeV on the energy axis, that hyperbola shows us all the possible form momentum values for, well, two components, time and x components, but all the possible form momentum values for a particle that has mass of 100 MeV, rest mass, if you want to think of it that way. And it's the particle mass 100 MeV, form momentum can go anywhere along this line and still have that mass. So, and that's because that mass is a quantity that's invariant across frames, while energy and momentum mix in funny ways. Okay, so what do I do with this? Well, what I want to do to use this diagram, I want to look at my various particles and spot where they are in the diagram. So for example, I have a kaon at rest. Mass equals 498. That means it has 0 x momentum. So for the kaon, what I want to do, I want to say along the 0px line, so right along this vertical line, I want to go up to nearly 500 MeV. I'll go just a smidge below. Clever way to put a dot there. And that is going to be the mass of my K0. The mass of my kaon is that 498 MeV point up there. Next, I've got a pion with a mass of 140 MeV. So I'm going to mark here. These boxes are each 25. So 100, 125, 150, 140 is going to be here. Here is the mass of my pion, sitting right there at 140 MeV. Problem is, that's just the mass of the pion. The kaon was sitting still, so that's where its form momentum is. It's right up there. Here, my pion, I'm at a momentum of 200 MeV. That means it's going to be at the 200 MeV point and a mass of 140 MeV. But remember, it's a mass of 140, not an energy of 140. So I can't just read straight across on this diagram to find my position. What I need to do is follow a hyperbola of constant mass as it angles up there. So let me just sketch that out. 140 is not a little above the halfway point of this. So I'm just going to sketch out where that slightly above halfway line can go. Oop, a little too low there. I'm just sketching out my hyperbola that is a bit above halfway. I'm probably not doing it very accurately. I could be better than this, but I've sketched out the hyperbola that corresponds to the mass of my pion. And what I need to do is take the 200 MeV mark up and follow it until it intersects right there. Maybe I can find some color to use. Here we go. Right around there is the point where the actual form momentum of my pion is. Again, all I did, I followed the pion's mass hyperbola up until I got to the x momentum that I expected. And I suppose I could jot down what that would look like. Let me grab this ruler. Let me just do a quick little line from the origin over to there to help us see what I'm doing, what I've done there. From here to there. Okay. So it's going to be hard for you to see, but I can see that I've drawn a straight line from the origin up to that point just to represent my form momentum. Need a darker pen. I've drawn that. That is the form momentum of my pion. Next, I look over here and I say my muon has a mass of 106 MeV. So here's 100, 125. About here is mass of my muon. And here, its momentum is in the negative x direction. So I'm going to follow a hyperbola over in that direction. Hyperbola from about here, close to the bottom, but not really right there. Try to follow the same fraction along this whole way. Okay, there's a hyperbola that I've drawn for my muon mass. So those are all different possible form momentum positions for a muon with a mass of 106 MeV. And my muon has momentum negative 80 MeV over c squared, so over c. So 0, 25, 50, 75, 80 is going to be about here. I'm going to follow that up until I hit this spot right there. Let me circle that in green again just to have that stand out a little. So I've got a spot here that is my muon. And again, let me draw just a little line to represent that since I sometimes visualize things well that way. Okay. My origin, my point up there. Okay, so I've drawn a form momentum line to represent this, to represent the muon's form momentum. There we are, two form momenta. And what I need to do now, I need to add them together. You can see, you can see that my energy of each one is above its mass value. The muon's energy is a little ways above its mass, just pure rest mass energy, and the pion is quite a ways over here. It's quite up high. So let me add these together. Okay, well, all I have to do is just basically move this line on top of this. I'm just going to add them just like I add vectors. Add, the tail of one connects to the head of the previous one. And so if I do that, let's see, I need to go, how high is this? This is almost up at the 250 mark. So I'm going almost 250 steps up, maybe a step down, 245 or something like that. So let me go 200 over from here. 1, 2, 3, 4, 100, 1, 2, 3, 4, 200, and then 250 up. Okay, I'll put there. 1, 2, 3, 100, 1, 2, 3, 200, 25, 50, little. Okay, so about here is the point I'm looking for. Let me draw a line there just for my own reference to spot where that's going. Okay, so again, the line I've just drawn to get up to this total of the two four momenta, the line I've just drawn is an exact copy of this four momentum just slid up to line up there. I've now added the four momenta, and boy, clearly this total four momentum of those two doesn't equal the four momentum of my last piece. What I'm missing looks like there is, what all am I missing? Let's see. I'm missing a line that goes over 1, 2, 3, 4, almost 5, and up the same amount. This is actually a nice 45-degree line if I follow that line up. So there's some missing energy and momentum in the two pieces that I found. It's not visible. Wait, over here. 45-degree line. Okay. So there's this missing piece. There's this missing piece right here that is my missing piece. I could even copy it down. What is that? I said it was 1, 2, 3, 120 or so, about 120, and it's at a 45-degree angle, so it's going to be 120, 120, about here. Here is my last piece that I have not done anything else with, and it comes right down there. My missing four momentum ends around here, and so the question over here was, is there anything missing? Was there anything else in my story? And my diagram, my energy momentum diagram has shown me, yeah, there's definitely something missing because I need this one extra piece that's going at a 45-degree angle on my space-time diagram. And you can ask, what mass do you have of a particle that's going at a 45-degree angle that has equal spatial and time-like components on an energy momentum diagram? That has to be a massless particle. By definition, only massless particles move along 45-degree angles. You can think about that as being a hyperbola that stretches all the way down here and asymptotes to 45 degrees very quickly. So I have a massless or nearly massless particle that's missing from my observations. And it turns out that massless particle, that missing particle, is a mu neutrino. It's a type of neutrino. It's a small neutral particle that has very close to zero mass. For a long time we thought it was zero. And here, this example, it has a four momentum that is 120 MeV or so in the negative x direction, 120 MeV of energy. So that's how I use this energy momentum diagram to do a conservation of four momentum problem. I'm just adding vectors on here in a very normal way. I just use those hyperbolas that are in this calibrated hyperbola paper. I use those hyperbolas to make sure that I'm getting the right mass and energy and momentum relationships. Okay, so that's how we do this with a diagram. How do I solve this problem if I don't have hyperbola paper handy, or if I want to do it more precisely than just reading things off of this graph? Well, what can I do? I can set up four momentum, energy px, py, pz, for all these different objects. Again, our notation in our class has been to call four momentum capital P, and the four momentum of our kaon, it's at rest, so px, py, and pz are all 0, and that means its energy is just equal to its mass. And so the four momentum of our kaon is going to be 498 MeV 0, 0, 0. Cool. Okay. What about our next particle? Our pion, four momentum for our pion, for our pi plus. Here, I know py and pz are 0, and I've been given that px is 200 MeV. What about the energy? Well, energy is the square root of p squared plus m squared. That's an x, really it is. Energy is the square root of p squared plus m squared, and as we look at p squared of p squared plus m squared, I have those values. I can say 140 squared plus 200 squared in MeV, And you know, I've actually done that calculation already. When I did that for the pion, I got 244 MeV, 200 MeV, 0, 0. How does that compare? 244, this was 250 at this point here. So yeah, that's about right. That corresponds to where the 200 line came up and hit my hyperbola. So the hyperbola paper paid off. It did exactly what it was supposed to. For momentum of our muon, I get in the same way, square root of p squared plus m squared. For that, p squared will be negative 80 squared. M squared is 106 squared in mega electron volts. And so when I did those earlier, save us some time, I got 133 MeV, and then I've got my minus 80 MeV, 0, 0. Okay, those are my 4 momentum values. And then, as I said, there's this mysterious neutrino as well, the missing 4 momentum that we can solve for. Putting all this together, the statement of conservation of 4 momentum is that 498 MeV, 0, 0, 0, that's that kaon at rest, has to equal 244 MeV, 200 MeV, 0, 0, that didn't work quite right, plus 133 MeV minus 80 MeV, 0, 0, plus, and here's my missing part, my energy of my neutrino, Px of my neutrino, and I can see those are going to be 0. Py and Pz of the neutrino have to be 0 because everything else is. So that's my equation. And I can look at that, and I can immediately solve to find those missing pieces. All I have to do is clear some space so I can write something. All I have to do is just solve for E of the neutrino. And writing that down, I'll find that E neutrino equals 498 minus 498 MeV minus 244 MeV minus 133 MeV. Adding these together is 133, really? Yes, this is 379. So that is 498 minus 379. Well, I can do it easily enough, but I'll embarrass myself. 498 minus 379 is 119. 119 MeV, and our Px from the neutrino is even easier. I can just look at that and say it's going to be minus 120 MeV. That's just solving for Px. And okay, so that means that my 4 momentum for the neutrino is 119 MeV and then minus 120 MeV, 0, 0. There's my 4 momentum in the neutrino. That's my missing piece, and it turns out that's not actually half bad. So obviously there's been some rounding error along the way because 119, the energy and momentum, the energy should never be less than the momentum for in absolute value for these things, or else you have an imaginary mass or something. But within rounding error of a couple spaces in the last place, you can see this is basically equal magnitudes in energy and momentum, which is the calling card of a massless or nearly massless particle. In this case, it would come out to be square root of some tiny negative number, but in the end, it comes out to be basically a massless particle. So this tells us that even though our particle detector did not detect the neutrino, it must have been there and it carried away some of the energy and momentum of the system. And again, that's very much what we drew in this picture. Very much what we found over here was 120 MeV in both directions, negative x and energy, that we were able to use, that we were able to spot there, corresponding to these equations. So the lesson from all this, the lesson that we take about 4 momentum, is that we can use an energy momentum diagram or we can use equations, but either way, all you do, you just take all the pieces you have before the interaction or the decay or the collision or whatever, and add up their four momenta, either as four vectors symbolically or as lines on a diagram. And then you take all the objects you have afterward and add up their four momentum, either as vectors, either as mathematical vectors or as lines on a diagram. Add them up as vectors here, and they have to add up to the same thing. Four momentum is conserved, and I won't try to prove it right now, but the fun part is this would be the same in any reference frame you looked at. If you boosted to a different reference frame, moving relative to where the kaon was flying by at high speed because it just came out of some other particle collision, well, you would find that these conservation law would still hold because four vector equations stay true in different reference frames. That's the lesson here, and I hope that it's a useful example of how to solve this kind of problem.